What's up, memers, dreamers, and lemurs? Welcome back. I've got a funny story to tell you. This is actually version 2 of this video. I think I got about 20 minutes into it, and then I realized I wasn't recording. And I looked over. I made a joke about how I'm like, I'm messing this up really bad. This is a disaster. It looks awful. It smells awful. It sounds awful. But we do it live. I'm not doing a second take. You're going to have to deal with the imperfections. And then I looked over to see how far into it I was, right? I was going to be like, I'm 20 minutes into this. I can't redo it. And I wasn't recording the whole time, you guys. I was acting to myself for 20 minutes. I was rehearsing. That's what we're going to call it. I was rehearsing. So now that I've got all the kinks worked out, let's do it for real. We're going to learn how to distinguish between conic sections. If my pen worked. My pen can't work. Of course it can't work. All right, now it works. So we're going to talk about distinguishing between conic sections. We're going to look at equations today, and we're going to say, that's a circle. That's an ugly circle. That's an ellipse. We've got some hyperbolas, and then we've got a parabola. So we're going to look at equations, and we're going to determine what type of conic section are we looking at. And then we're going to find the important information for it. We might find the vertex. We might find the semi-major and semi-minor axis. We might find the center. We'll find all that good stuff. So before we dive into looking at examples, let me talk at you for a little bit and refresh your brain chemistry about the cool features of all of these things. So the features of the two most common or most what's the word I'm looking for here, you guys? The most familiar conic sections, the ones we're most acquainted with. We walk into a party, we grab a soda pop, and then we beeline it for circles because we're homies with circles and we're comfortable talking about how awkward we are at parties with circles. So circles have both the x and the y squareds terms squared. So if you see an x squared and a y squared, it might be a circle. It's not a dead giveaway, but it could be a circle. The other thing we need to know about circles is that if it's written in vertex form and it's equal to 1, which it probably won't be, but a boy can dream, the denominators will match. And we'll talk about this a little more when we talk about ellipses. The x squared and the y squared terms must also both be positive, like this. We can't have a negative in front of one of them. If we do that, it's not going to be a circle anymore. All right, so there's circles. Quadratics. If circles are our homie that we go find at the party because we're awkward, quadratics are the party host's dog. If we can't find the circle, we beeline it to the dog because we don't have to socialize with a dog. Our social anxiety won't get the best of us. We just pet it because it's a dog and it's just happy someone's paying attention to it. So quadratics are the easiest thing to socialize with or to identify. Quadratics are easy to identify because only the x term will be squared. You're going to have x squared and then no y squared, just x squared. You might have some x's in there. You might have a y in there, but no y squareds. If only the x has a squared term, parabola. All right, let's talk about the two least familiar ones. These are like new people you've got to talk to and be like, all right, so what are you into? Do you like coloring like I do? So let's talk about ellipses. Ellipses, both the x and the y will be squared. The x squared and the y squared will both have positive coefficients. This is what sets them apart from hyperbolas. But so far, this looks a lot like circles. Both of them are squared, both of them are positive. The thing that sets ellipses and circles apart from one another are the denominators will be different when it's in vertex form. What this means is that the radius of our circle this way will be different than the radius of our circle this way, and that's what turns it into an ellipse and makes it an oval. So we have to have different length, horizontal and vertical axes. If they are the same, if we have an oval and the oval is the same length this way as this way, it's a really circular oval, isn't it? It's kind of like this. So there we go. Hyperbolas are the last one. Again, we will have x and y squared. This is why quadratics are so easy to find. It's the only one without them both squared. And the x and the y term will, either the x or the y term will have a negative coefficient. Only one of them. So we might have x squared minus y squared, or we're going to have y squared minus x squared. Usually the negative one will come second. You're going to say, Mr. Barton, what about the denominators of hyperbolas? Are they the same or are they different? Well, they could be either. If they are different, it just means our hyperbola is going to be really stretched out like this. If they're the same, then our hyperbola would be a little more symmetrical in the x and y directions. So the denominator of hyperbolas, because it's talking about our transverse and conjugate axes, these two numbers are going to stretch it horizontally or stretch it vertically. But if they're stretched the same amount in both directions, then your hyperbola is going to look a little squarish. But that's a-okay. That can happen. All right. Let's talk about the a and b for ellipses and hyperbolas, because the a and the b can be a little bit confusing. So let's just talk about them one more time so that they're fresh in your brain. For ellipses, A is going to tell us our semi-major axis, meaning the longer axis of our oval. And B is going to tell us the semi-minor axis, so the shorter distance across the oval. The order of the terms does not matter. So you could either have A squared and then B squared, or these could swap and you could have b squared first, then a squared. It doesn't matter. The way you tell which one is which is a is always going to be the bigger number. So if we have over 16 and then over 9, this is the a term because it's a bigger number. For hyperbolas, 2 times a is going to tell us the length of our transverse axis. Which might seem weird, right? Why do I need to multiply this by 2? The word semi means half. This is maybe like the major radius and the minor radius. When we say semi-major axis, we're talking about diameters. So these will tell us radii. These will tell us quote-unquote diameters, or the total distance across. So that's why we times 2. So A tells us the transverse axis. 2 times B tells us the conjugate axis. Our transverse axis, if we're looking at a hyperbola like this, the transverse axis cuts it in half. The conjugate axis is going to be the one that reflects it, or goes right between the hyperbolas, but doesn't touch either of them. So transverse cuts it in half, conjugate reflects. A is always going to be under the positive ratio or the positive fraction. So this first fraction, it might be x minus 2 squared over 16 minus y plus 3 squared over 25. It doesn't matter that 16 is smaller. A is under the positive one. There's a plus sign in front of this. B will always be under the negative ratio. So this would be b squared. This is a squared. The size of them is irrelevant for hyperbolas. All right, let's look at some examples. So for this first one, we're going to look at it and we're going to start checking our terms. The very first thing we should always look for is, do I have x squared and y squared? There's x squared. Oh, no y squared. So this is going to be a parabola. Cool. Parabola. We did it. We found it out. So that's kind of boring though. Let's figure out some stuff about the parabola. Let's find its vertex. So before we get going, I need the disclaimer. This is supposed to be a negative right here. I can't change it. This is a picture of an equation. Look, it's a picture. It's all together. So pretend it's a negative. So for our parabola, we're going to move our y over. So it's y equals an equation. So we're going to have x squared plus 2x plus 1 equals y. Now there's two ways for this problem that we could find our vertex, which is going to be, if we look at a parabola, it's this point right here at the bottom of the u. It's the minimum. So to find our vertex, there's two things we can do. We can use this equation, x equals negative b over 2 times a, if it's in standard form like this. So b is just the coefficient of the linear term. So we would have x equals negative 2 over 2 times a is the coefficient of our squared term, times 1. So this is negative 2 over 2, which is negative 1. That's one way we could find the x piece of our vertex. The other way is this is factorable. It just happened to be factorable. It was an accident. So we could factor it. This will be x plus 1 times x plus 1 equals y. And then we could, oh, look, it's the same thing. We could write it as x plus 1 squared equals y. So our h value is negative 1. Oh, that's tight. Oh, sorry, negative 1. I'm missing my negative up there. Okay. Now to find the y value right here, what we need to do is plug this number back into this equation. You're saying, Mr. Barton, let's just look at the k plus 0. Okay, so it's 0, but let's plug it back in just to make sure everything agrees and math works. So if I plug negative 1 in here, we're going to have negative 1 squared plus 2 times negative 1 plus 1 equals y. This is 1 minus 2 plus 1 equals y. 1 plus 1 is 2 minus 2, that's 0. So y is 0 just like we thought. So there's our parabola. There's our vertex. I think that's all you're going to need to know. It's a shame we don't talk about the focus. Those are cool, but oh well. All right, now we're going to look at this one. So looking at it, all right, we've got an x squared and a y squared. So it's definitely not going to be a parabola. Okay. Can you guys tell if this is a circle or not? I'll give you a hint. It's not. The reason I can kind of tell it's not a circle is because my x squared and my y squared have different leading coefficients. Okay. So that it's probably, I think, or I know, but you think, we're thinking together that because that coefficient is different, maybe when I do my completing the square and stuff, the denominator number, when I simplify, is going to be different because I'm going to have a 4 in front of my x's and I won't in front of my y's. So it's probably not going to reduce the same. The other thing I can notice is that this is positive and this is positive. So they're both going to be positive. So if they're going to be x squared plus y squared, and I think this number is going to be different than this number. What is that? That's an ellipse. So this is going to be, whoops, how do I spell? Ellipse. There we go. This is an ellipse, but let's go ahead and do the math just to prove to ourselves that it's an ellipse and to find some of the important information. So we're going to group our x's together. We're going to have 4x squared minus 8x plus blank to complete the square. Then we'll group our y's together. We have y squared plus 6y plus blank equals 23 plus a red blank plus a blue blank. Now we need to factor out our coefficients of x's and y's. So here we can take a 4 out. So 4x squared minus 2x plus blank. I haven't put anything here yet, so I don't need to take a 4 out of this. It's not there. It doesn't exist yet. So I'm not going to worry too much about that. I'll put it in the parentheses. Plus, we don't need to factor anything out. We could put a 1 there if you want, but this will just stay the same for right now. Plus y squared plus 6y plus blank equals 23 plus blank plus blank. All right. Now these blanks are all here so we can complete the square. So we need to factor this. We're not doing anything with the 4. We're just rewriting our parentheses as x with something squared. To get the something here, we divide the coefficient of the linear term by 2. So half of negative 2 is negative 1. We square the negative 1 to 1. And now we multiply this new number we just added to the coefficient. I'm not adding 1. I'm adding 1 times 4. So we're adding 4 on both sides. Then we repeat that process with our y's. So we have plus y and something squared. Half of 6 is 3, so plus 3. 3 squared is 9. There's not a coefficient here, so we just add 9 to the other side to be safe. Equals, now we simplify this. 23 plus 9 is 32, plus 4 is 36. Looking good so far. Now to get this into vertex form, we have to make this equal 1, so we divide both sides by 36. Okay, these cancel and equal 1. This doesn't simplify at all. Y plus 3 squared over 36 plus 4 over 36 reduces to 1 over 9. X minus 1 squared. So now we have all the information we need. Our center is going to be at 1, negative 3. Remember, we have to change the signs of h and k. Our a, for ellipses, it's the square root of the bigger denominator. So we're going to be looking at this right here. Square root of 36 is 6. So this would be our semi-major axis. And then b is the square root of the smaller number. So square root of 9 is 3. So our ellipse is going to be 6 tall because our major axis is with the y. It's going to be 3 wide. It'll actually be 12 tall. If we look at an ellipse, the semi-major tells you from the middle to the farthest point, and the semi-minor tells you from the middle to the farthest point. So this will be 6, this will be 3. The whole thing will be 12 and 6. So there we go. There's all our information for the ellipse. 2 more. All right, we're looking at this. We have an x squared and a y squared. So it's not a parabola. They have different leading coefficients. So it's not a circle. And one of their leading coefficients is negative. That means this is going to be a hyperbola. Hyperbola. So we figured out what it is. Ding, ding, ding. We're done. Next homework question. Next homework question asks us for the transverse and conjugate axes. So let's do all the work. Group our x's together. Negative x squared minus 4x plus blank. Group our y's together. Plus 4y squared plus 24y plus blank equals 32 plus blank plus blank. All right. Now we need to factor out our leading or our coefficients from our variables. So the x, I'm going to take the negative out. So I'm going to have negative 1, x squared minus plus 4x plus blank. And for the y's, I'm going to take the 4 out. So plus 4 y squared plus 6y plus blank equals 32 plus our blanks. All right. Now we need to figure out what goes in these blanks. So we complete the square. So bring down our minus 1. X and something squared, half of our linear term is 2. So x plus 2. 2 squared is 4. 4 times this coefficient is negative 4. Now our y's. Bring down our plus 4. We have y squared. Whoops, sorry. The square goes outside. Plus 4. Y and something squared will give us this. We take half of the linear term. Plus 3. Square this is 9. 9 times 4 is 36. All right. Equals, simplify. 32 minus 4 is 28, plus 36 is 64. And now we have to do a couple of things just to make this look nice. The first thing is for hyperbolas, the negative term generally comes second. So we're going to switch the order, and we're going to divide everything by 64. So these cancel and equal 1. Let's put this stuff in front. 4 goes into 64 16 times, I believe. So we're going to have y plus 3 squared over 16 minus 1 and 64 don't reduce. So x plus 2 squared over 64. So now our transverse axis is going to go with the y. It's always the leading denominator. Square root is 4 times 2. Transverse axis equals 8. Our conjugate axis is always with the negative term. Square root of 64 is 8 times 2 would be 16. And then our center is going to be at negative 3, negative 2. All right. Pretty easy. Or maybe not. Maybe a little hard, but it's all right. You're big kids. I believe in you. All right. Last one. This one, by process of elimination, must be a circle. But let's see why it's a circle. We have x squared. We have y squared. Their coefficients are both 1s, so they match, and they're both positive. If one of them was negative, even if they matched, it would be a hyperbola. But because they're both positive and they match, it must be a circle. So let's do the completing the square process one more time just so you get the full set of notes. So we have x squared plus 6x plus blank plus y squared plus 6y plus blank equals negative 9. Complete our square. So we're going to have x and something squared is this. Half of 6 is 3. So plus 3, square that is 9. We're going to put plus 9 on this side too. Same thing here. Plus y divide by 2 plus 3 squared. Square the 3 is 9 plus another 9. So these cancel and equal 9. We can just leave this like this because circles we don't want to divide. We could just actually let's do it. Let's divide by 9 just so that we can kind of see how it looks. So if we divide by 9, divide by 9, divide by 9, this here cancels out. Oh, that's not an eraser. N equals 1. So this looks very much like an ellipse now, but we notice our semi-major and semi-minor axes have the same number, so it's equally wide as it is tall. So there we go. All right, there's your notes for identifying the difference between conic sections. You guys, I think I have an idea for if I can get to 200 subscribers. I think I'm gonna have a special video. But we gotta get there first. So don't make sure. Do the opposite of that. Make sure to like and subscribe. You know what else would be tight? Share this with people. Take this video and say, you know what? My math teacher is one of the coolest people I know in the whole world. I want to be just like him when I grow up. And I want all my friends to be just like him when I grow up. So I'm going to share this video to all those other pre-cal students around the world in need so that his good word can spread across the globe. And then we can get to 200 subscribers and I'll make a funny video, I swear. Until next time, have a great day.